Hi everybody. So this next section, and I believe this is the last section for chapter. No, I guess there's one more section. I guess. The last section for chapter, or the second to last section, the penultimate section for section 4 point or chapter 4 is 4.7 on Newton's method, and this is a numerical method for finding the solutions to equations or finding roots or zeros or whatever you want to call them. And the idea behind Newton's method is it exploits what we know about calculus. Let's say, for example, that you're trying to find this root, right? So you have this function, you know it crosses the x-axis, but you're not exactly sure where. Let's say maybe you have some idea. What you would do is pick a point nearby the root, like maybe this point, and then what you would do is you could use some ideas from calculus to try to find that root. So what you would do is go up to the function, draw the tangent line. The tangent line should intersect the x-axis somewhere else. Just draw a line up to the curve, draw another tangent line. This will give you a better approximation to the root, and then you can keep doing that over and over again as many times as you want to find that approximation. I suppose this is called Newton's method because Newton was one of the first people who knew calculus and exploited its power to do lots of different things. Now there are some things I should warn you about when it comes to Newton's method. Some caveats. We'll talk about that here in just a minute. But so basically, what you're going to do, and like I said, this is an iterative process. What you're going to do is take this formula where you're basically taking the next estimate of the root, which should be equal to the previous estimate of the root minus the function divided by the derivative, right? And I guess the reason why that's true is if you look at the equation of this line, right, the tangent line to the equation is y minus x sub n, right, because that's the point on the y-axis, and then it's the slope times x minus x sub n. So this is just the point slope form for the equation. And then if you sort of rearrange that, right, divide both sides by f prime of x sub n, that'll basically give you this formula, right? So maybe just to show you where that's coming from, right? If I take this equation, I'm looking at the x-intercept here also, right? If I take this equation, y minus f of x sub n is equal to the slope of x sub n times x minus x sub n, right? That's the equation of this line. When I hit the x-axis here, right, remember we're trying to approximate this root. This thing here that we're finding is the x plus n root. In that particular case, right, the x-coordinate would be 0, right? So plugging that value in for x, right, you have y minus f of x sub n is equal to f prime of x sub n times x sub n there. And then if I divide both sides by f prime of x sub n, right, I'll get y. I'm sorry, the y coordinate there is 0, right, not the x coordinate. Sorry, that should be 0. So you'll still have the x in here, right, because the height of the point is 0. So if I divide both sides by f prime, right, I'll have f of x sub n divided by f prime of x sub n. That should be equal to x minus x sub n, right? And then the x-coordinate of that point is this, so if I subtract x sub n from both sides, right, I'll get this, and the x-coordinate of that point, which is the next iteration, is given by that, right? In case you're curious as to where this equation is coming from, right? I mean, again, you could just sort of memorize it or put it on your formula sheet, but it basically comes from the equation of that tangent line. So just to outline Newton's method here in a couple steps, right? You guess a point, right, that's close to your solution, right? So you guess a first approximation solution to the equation. and then use the first approximation to get closer and closer to your root. And the idea again behind this is it's an iterative process. The output of this you keep plugging back into the same formula over and over again. So iterate just means to take your output and plug it back in as input again. So let's say, for example, we have the curve x cubed minus x minus 1, and we know that the graph crosses the x-axis once, right? Where is it, right? I mean, we have a rough idea of where it's going to be, right? Somewhere between 1 and 2, closer to 1 than 2. So, maybe it's 1.3, but let's say you need a really accurate answer there. You could do Newton's method as many times as you want to get closer and closer to that root. So in this particular case, let me just run through a numerical example here, and then maybe I'll do the calculations. So in this particular case, right, you would maybe choose x sub 0 is 1, right? So 1 is pretty close to that root. It's hard to tell where it is, right? Maybe you could choose 1.1. I'm just picking 1 in this case. And then the second guess will be 1.5, which should be even better. And then the third guess will be 1.3478, right? The idea is that it should get closer and closer to the root there. And so now if you choose a different starting point, like let's say you chose 3, you might get a different value for each one of those terms, but the more and more you do it, right, you should get closer and closer to the value of the root there. And again, you can see that these are off a little bit, right? This is 1.347. Here I've got 1.6. So if I want a better idea of what this root is, right, I might, I might want to try Newton's method a couple more times, and then I might get even closer to that root, right? So it's probably the 1.3478 is probably a better approximation. So the only difference is if you start with a different number, is you may have to go through more iterations to get closer to the point that you're at. So the closer you can start to the root, right, the better, right? So 1 is closer to the root than 3 is. So here's the numerical table for this, right? So so for the derivative of this, you would just have 3x squared minus 1, right? So for Newton's method in this particular case, right, if you remember the formula, let me maybe just write it down up here. Right, so x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So in this particular case, that's going to be x sub n minus the function, right, which is going to be x sub n cubed minus x sub n minus 1, top over the derivative, right, which will be 3 x sub n squared minus 1. And so the idea again in this case is you would just start out with n sub 0, right? Plug that in, get your answer, and then take that and keep plugging that back into the equation over and over again, right? So I'll start out with my x sub 0 will be 1, so I'm going to start by making this a 1, all the x sub n's a 1, so that'll basically give you 1 minus the top, which will be minus 1 over the bottom, which is 2. So what's 1 minus negative 1 over 2? Well, that'll be 1.5, right? Then you take 1.5, and then you plug that in for x sub n. So it'll be 1.5 minus 1.5 cubed minus 1.5 minus 1 over 3 times 1.5 squared minus 1. So take that minus that divided by that should give you that, right? Then take that and plug it in, and again, you'll see that as you do that over and over again, right, you should get closer and closer to the actual root. So let's do an example. Well, actually, let me kind of maybe talk through the rest of this example here with the calculations, right? So again, you'd start out with, well, I guess this is a little bit different, right? Here we're starting out with x sub 0 is equal to 0, not 1. Right? So, but again, you should get closer and closer to the answer there. And and I guess this is a slightly different equation. Sorry, I thought these were both minuses, right? But they're both plus. So, and a lot of times you'll have to let Newton's method run until you get a certain degree of accuracy. But typically on the exam or something, I'll just tell you to find x sub 2, and I'll also tell you typically what point to start with, because everybody's going to wind up with a different answer. So the idea in this case, again, is you just plug into this equation, right? So the top is this, the bottom would be the derivative, which would be 3x squared plus 3. So start with x sub 0, right? Wherever you see an x sub n, plug zeros in there, right? That gives you negative 1/3. Then take negative 1/3 and plug that in for all the x sub n's. Work that out, that'll give you that value. And that is all the further I wanted you to go, right, is negative 0.322. Now, as far as how close that is to the actual root, you know, I guess you'd have to know the actual root in that case. But you can keep calculating this until the decimal places are the same. So if you wanted to compute this so that you're accurate to the first, say, 4 decimal places, you would just keep computing until the 4 decimal places remain constant, right? So here's another example. Now in this case, this particular problem is factorable, so you wouldn't have to use Newton's method. You could just factor it, or use the quadratic formula, right? I guess for this one you couldn't use the quadratic formula because it's cubic. Let's use Newton's method instead. So we want to start with x is equal to 0, and we want to look at the left limit. So in this case, or the left root. Right, so we've got 0, so 2 is over here, negative 1 is over here, right? This is 2 is one of our roots, negative 1 is the other root. And we want to do this for the left, so we're starting out here at x is equal to 0, and we're trying to find this one, right? So the idea is hopefully this will get closer and closer to negative 1, and again, we only want to find x sub 2. So plugging into the formula for Newton's method, right, I take the derivative to get the bottom. I start out with x sub 1, and I guess I should, hopefully I'll be clear about this on the exam, right? What, whether you start out with x sub 1 or x sub 0, I guess. But let's say you start out with x sub 1. I guess it doesn't really matter what you call the index, but so in this case you plug in 0 here, and that'll give you negative 1/2 for the first approximation, right? Negative 0.5. So you can see it gets a little bit closer, right? We started at 0, we're at negative 1.5. Or negative 0.5, and then I would plug in negative 1/2, and then hopefully that should give you a better approximation. I'm not sure if that is better though, so maybe I made some mistake in here. I'll have to double check that. But so the idea again is you in this case I just told you where to stop, so you could stop there, but I suspect I made a mistake because again, if this is if this is negative 0.5, this should be closer and closer to negative 1. So maybe I'll have to double check my arithmetic there for that one. Another place you can use this for is to try to find points of intersection. So let's say you want to figure out where these two graphs intersect. Well, just take one minus the other and just set it equal to 0, right? So just take one function minus the other, and then you'd be trying to find out where that difference is equal to 0. So the derivative of this function is that, so plugging into Newton's method, I'm going to just start with x sub 0 is equal to 1. Again, I just happened to pick that, right? I mean, it looks like it's at about 1.335. So go ahead and plug that in, right? You'll get 1.4, and then take that result, plug it back into the formula again, and that gives you 1.3556. So again, that does give you a pretty good estimate. Now in this case, I guess I kind of cheated because I graphed the function in advance, but let's say we didn't know the graph, right? That gets you pretty close to what the root would seem to be. One thing to just warn you about, in some cases Newton's method does not work very well. Most of the problems I give you, they should pretty much work, but there are a couple of weird things that can happen. One is you could have a situation like this where you have a curve where you get a point, and then you draw the tangent line, you get another point, and then it just keeps circulating back and forth between the 2 points, and you don't get any closer to the root. A couple other things that can happen is you may accidentally find the root you're not looking for if you have 2 different roots. For example, like let's say this is your starting point. and you're trying to find this root, right, you could have a situation like this where it might zoom into another root. So you, again, if you have two roots like this, you want to make sure that you start closer to the one root you're looking for, right? Or you could have a situation like this where you start with this, again, you're trying to find this root, and you get something like that. So even if you do start closer to the other root, it may accidentally find the other root also. So just a couple things to be aware of. But that shouldn't happen on the homework of the exam. If I do give you a problem, you know, I'll tell you which point to start with and how many iterations to go through. But in real life, again, you'd have to go through as many iterations as you want, right? So if your boss says find the root to this equation to 4 decimal places, you'd have to keep doing the iteration for Newton's method over and over again until you get that the answer is the same to 4 decimal places. Okay, so the next section, we're going to kind of start to move into the second part of calculus. We've kind of been flirting or hinting with this all along, but what we're going to look at in the next section is antiderivatives. And like I said, the first part of calculus was how to calculate using slopes and things like that. And like I said, we're pretty much done with that. If you remember, the second part of calculus, like I said, has to do with calculating areas, and that's kind of what we're moving into. We'll kind of give you a taste in 4.8, and then we'll really move into it in Chapter 5. So we're sort of done with the first part of the class after this section. So, all right. Well, if you guys have questions, as usual, let me know.